Okay, Assalamualaikum and good morning class. Okay, today in our lecture, I'm going to discuss topic 6, alternating current, yeah. Okay, so for the learning outcome, so you can read it in your tutorial book or your lecture note. Okay, before we start the details, so let's take a look to the mind map of this topic, yeah, alternating current. Okay, so the first part is we have the AC waveform. Okay, under AC waveform, we have root mean squared current. Okay, root mean squared value, which is we have root mean squared current and also root mean squared voltage. Okay, the second part, we have a phasor diagram. Okay, there is a 6 type of phasor diagram. First, pure resistor, pure capacitor, pure inductor, RC circuit, RL circuit, and also RCL circuit. Okay, so each circuit will have a different phasor diagram and also different equation, yeah, according to the RCL, RC, RL or RCL. Okay. Okay, the last part we have power. So divided into 3 parts: average power, instantaneous power, and also power factor. Okay, so that's the thing that we are going to discuss here on today's lecture. Okay, alternating current AC is defined as the electric current, okay, whose magnitude and direction change periodically. Okay, under AC waveform we have root mean squared value. Okay, root mean squared value, root mean squared RMS value of an alternating current is equivalent. Okay, direct current DC which produce the same power dissipation in a given resistance. So I direct current equal to I RMS for the alternating current. Okay, so definition for the root mean squared current, okay, is defined as the value of the steady direct current which produce the same power in a resistor as the mean average power produced by the AC. So that is the definition for the root mean squared current. So RMS, okay, this is the equation related to the root mean squared current. So RMS equal to I naught divided by Z2. Okay, so I naught will be the peak current. Okay, I naught will be the peak current, yeah. Okay, peak current. So RMS is a root mean squared current. Okay. Alright, so we have root mean squared voltage, okay, VRMS. So it's defined as the value of the steady direct voltage, okay, steady direct voltage, when applied across a resistor, produce the same power as the mean average power produced by the alternating voltage across the same resistor. So that is the definition for the root mean squared voltage, VRMS. Okay, equation for the VRMS. So VRMS equal to V0 divided by Z2. So V0 is the peak voltage. Okay, V0 is the peak voltage. Okay, V0 is the peak voltage. I0 is the peak current. Okay, then we have average power. Okay, general formula for the average power. So P average equal to RMS squared R. Okay, average power. Alright, okay. So the other formula for the average power, okay. So average power in RCL circuit, so P average equal to IVR equal to I squared R. Okay, the first equation. And then after we do the it can be modified into, okay, P average equal to I squared Z cos phi equal to PR. Okay, so this is the second formula for average power. Okay, cos theta is called the power factor of the AC circuit. Okay, so P average equal to I squared Z cos phi equal to PR. So PR is the average real power. Okay, so I squared Z is called the apparent power. Okay, so that's a few equation involving average power in RCL circuit. Okay, next we have instantaneous power. So P equal to IV. So equation for the instantaneous power. Okay, then we have power factor. Okay, so power factor is cos phi ataupun cos theta. Okay, cos theta is the power factor. So the first equation is PR equal to I squared Z, or you can use PR equal to PA. Okay, or you can use cos theta equal to VR over V. Okay, ataupun equal to IR over IZ. Okay, or cos phi equal to R over Z. So PA is the apparent power. So I squared Z equal to IV. Okay, so this is a few formula involving average power, instantaneous power, and also power factor in RCL circuit. Okay. Okay, now let's take a look to a few definition and concept that we have in this topic for the AC circuit. So we look at the first part first. Okay, so alternating current is defined as an electric current whose magnitude and direction change periodically. Okay, frequency F is defined as the number of complete cycle in 1 second. Okay, then we have the period T is defined as the time taken for one complete cycle. Okay, then we have the peak current. Okay, peak current is I naught. Okay, is defined as the magnitude of the maximum current. Okay, then we have mean or average current. I average is defined as average mean value of current in a half cycle flow of current in a certain direction. Okay, then we have root mean squared RMS current. Okay, so root mean squared RMS is defined as the value of the steady direct current, okay, which produce the same power in a resistor as the mean average power produced by the AC. So this is the equation for the RMS. So RMS equal to I naught divided by Z2. So I naught will be the peak current. Okay, as I told you before. So I naught is the peak current. Okay, so sometimes they will give you a graph, graph of I against T. So you must know how to find all the information that you need, okay, from the graph. Alright. So this is a graph of sinusoidal graph for the current against time in alternating current. Okay. So the highest part ni we called it as a peak current. Okay, peak current or maximum current. Okay, the value here, this is the peak current or maximum current. Okay. Okay. And then below this one is the IRMS. Okay, root mean squared current. So IRMS equal to 0.707 I naught. Okay, so this is the IRMS current. Okay, this is the peak current. Okay, so then we have the sinusoidal graph. Okay, so one complete oscillation represent the period. Okay, one complete oscillation represent the period, period. Okay, so from this period you can find the frequency by using formula omega equal to 2 pi over 2 pi f. Okay, omega equal to 2 pi f ataupun 1 over T equal to 1 over f. Okay, ada one ada. Okay, T equal to 1 over f, or you can use, okay, or you can use omega equal to 2 pi f. Okay, so this is some knowledge or information that you must know in order to solve the question involving alternating current. Okay, alright. Okay, next we have root mean squared RMS voltage and its formula. Okay, root mean squared voltage V RMS is defined as the value of the steady direct voltage. Okay, steady direct voltage which when applied across a resistor produce the same power. Okay, produce the same power as the mean average power produced by the alternating voltage across the same resistor. Okay, so that is the definition for the root mean squared voltage. Okay, So we have equation here, VRMS equal to V0 divided by Z2. So that will be the equation for the VRMS. Okay, we also have the graph of V against T. Okay, graph of V against T. So the highest part ni, this is the peak voltage. Okay, below, a little bit below before the first is the VRMS. Okay. Okay, root mean squared voltage. Okay. And then one complete oscillation supposed to be will represent the period. Okay, one complete oscillation represent the period. Alright. Okay. Okay, then we have the phasor. Okay, phasor or phasor diagram is defined. Okay, phasor is defined as the vector that rotate anti-clockwise about its axis with constant angular velocity. Okay, so this is the definition for the phasor diagram. Okay, then we have impedance Z. Okay, impedance Z is a quantity that measures the opposition of a circuit to the AC flow. Okay, so unit for impedance is ohm, yeah. Okay, the equation is Z equal to VRMS divided by IRMS. Okay, so Z is the total impedance. Okay, Z is the total impedance. Okay, then we have pure resistor. Okay, pure resistor means that no capacitance and self-inductance effect in the AC circuit. So a circuit that contain resistor only. So we call it as a pure resistor. Okay. So pure capacitor means that no resistance. Okay, pure capacitor means that no resistance and self-inductance effect in the AC circuit. Okay. So pure resistor refer to the circuit which only have capacitor only. Okay, so that was a pure capacitor. Content only capacitor, pure capacitor. Content only resistor, pure resistor. Okay, content only capacitor. So the circuit will be pure capacitor. Okay, from the capacitor we have capacitive reactance. Okay, so capacitive reactance is the opposition of a capacitor due to the alternating current flows. Yeah, so the unit also ohm. Okay, so this is the equation for the capacitive reactance. Yeah, so we use C there. Okay, so at C equal to 1 over 2 pi Fc or omega C. Okay, so that is the equation for the capacitive reactance. Okay, then look at pure inductor. Okay, pure inductor means that no resistance and capacitance effect in the AC circuit. So pure inductor contain inductor only, yeah, in the circuit. Okay, then we have inductive reactance. Okay, inductive reactance is the opposition of inductor to the alternating current flow. So unit is ohm. Okay, so unit for inductive reactance is ohm also, yeah. Okay, so the equation is SL equal to 2 pi FL. Okay, so SL is the inductive reactance. Okay, XC is the capacitive reactance. Okay, alright. Okay, so that is the first part of alternating current. Okay, the details ni I will continue later, yeah. Alright. Okay, now look at the circuit first, the circuit that we have in this topic, yeah. Okay, let's continue with the discussion of the first three, yeah, types of the AC circuit. Okay, first we have the pure resistor. Okay, pure resistor is a circuit consists resistor only. Okay, consists resistors only, so we call it as a pure resistor. Okay, then we have pure capacitor is a circuit consists capacitor only. So then it become pure capacitor. Okay, then we have pure inductor. Okay, pure inductor is the circuit contain inductor only. So then it become pure inductor. Alright. Okay, so the concept here is, okay, for the pure resistor, both current and voltage are in phase. Okay, both current and voltage are in phase. Okay, so both of them start from the same point, 0, yeah. Start from 0. So both current and voltage are in phase. So V equal to, okay, equation for the voltage, okay, because this is the sine graph, yeah. So V equal to V naught sine omega t. Okay, and for the current, I equal to I naught sine omega t. Okay, so both current and voltage are in phase. So means that when there is a current, then there will be a voltage. Okay, no current, no voltage. So for for resistor. Okay, so no current, no voltage. Okay, so both current and voltage are in phase. Okay, in phase. So both of them, the graph will start from 0. Okay, now look at the pure inductor. Okay, pure inductor. In pure inductor, the current lead the voltage by 90 degree or 1/4 cycle. Okay, for the pure capacitor, current lead voltage. Okay, current lead voltage by 90 degree. So this is the current. Current start first and then followed by the voltage. So in this case, current lead voltage by 90 degree. Okay, so when they ask you to build up the equation for the voltage, so as we can see here, okay, the voltage start from 0. Okay, so the current is, we just use the usual equation, yeah. So V equal to V naught sine omega t. Okay, if the current start from 0. If the voltage start from 0. So V equal to V naught sine omega t. Okay, for the current, as we can see here, so current start at one value. Okay, at one value, yeah. So current start here at one value. Okay, alright. So then the graph, the equation of the graph will become I equal to I naught sine omega t plus pi over 2. Okay, so I equal to I naught sine omega t plus pi over 2. Okay, so why we have pi over 2 at the back? Because it doesn't start from the origin. It start from the 1 point, yeah. Okay, so pi over 2. Okay, pi over 2, yeah. So the current lead voltage by 90 degree. So current go first and then followed by the voltage. Okay, then we have the pure inductor circuit. Okay, pure inductor circuit is circuit containing inductor only. Okay, so the concept in pure inductor is the voltage leads the current by 90 degree or 1/4 cycle. Okay, so in this case, voltage lead current. Okay, look at the graph. Ya, nampak ya, voltage go first and then followed by the current. So voltage lead current by 90 degree. Okay, so when you ask to write the equation, okay, for the current example, okay, this current, so it start from 0. So I equal to I naught sine omega t. Okay, okay, next, okay, for the voltage, okay, look at the voltage here. Okay, voltage here also start from the 1 point. Okay, so the equation will become V equal to V naught sine omega t plus pi over 2. Okay, so pi over 2 because at the back it start voltage leads the current by 90 degree or 1/4 cycle. Okay, so this is the current for the voltage, yeah. Okay, voltage. Okay, so okay, next look at the equation, yeah, that we can build up lah. Okay, equation that we can build up. No need to remember so much. Okay, so sometimes there is equation that you can build up on your own, right? Okay, so now build up equation for the impedance. Okay, impedance is Z. Okay, for the pure resistor, so VRMS Z equal to VRMS divided by RMS dan V naught divided by I naught. So Z equal to R. Okay, since in the circuit only have R only. Okay, okay. So Z equal to VRMS over RMS equal to V naught over I naught equal to R. Okay, then tengok for the reactant and impedance, look at the pure capacitor graph. So pure capacitor graph, we have C, and then from the C it turned out to be HC. Okay. So HC equal to omega C. Okay. Equal to also 1 over 2 pi FC. Okay, omega equal to pi F, right? Okay, time with C, ya, the value of the capacitor. Okay, this for the pure capacitor. Okay, and then for the pure inductor, we have SL. Okay, SL equal to omega L or 2 pi FL. Okay, so this is the equation for the impedance or reactant, ya, for the pure resistor, pure capacitor, and also pure inductor. Okay, so equation for the VRMS, so VRMS equal to IRMSR. For pure resistor, okay, pure capacitor, VRMS equal to IRMS at C. Okay, then for the pure inductor, VRMS equal to IRMS at L. Okay, so this is value for the VRMS. Pure resistor, pure capacitor, pure inductor. Okay, for the general voltage V, okay, general voltage V ataupun total voltage, for pure resistor, V equal to IR. Okay, pure capacitor, VC equal to I at C. And for the pure inductor, VL equal to I at L. Okay, XL, inductive. Okay, at C, capacitive reactant. SL, inductive reactant. Okay, then for the maximum voltage, V0. Okay, V0 equal to I0 R0. Okay, for the pure resistor. Okay, V0 equal to I0 over omega C, or V0 equal to I0 at C for the pure capacitor. And then V0 equal to omega L I0 or I0 SL. So this one is the for pure inductor. Okay, maximum voltage. Okay, then for the maximum current, just modified from this equation above. So I0 equal to V0 over R0 for the maximum current for the pure capacitor. I0 equal to omega C V0, maximum current for the pure capacitor. And I0 equal to V0 over omega L. Okay, maximum current for the pure inductor. Okay, now look at for the instantaneous power. Okay, for the for the pure resistor, so P equal to I0 V0 sin squared omega T. So P average equal to I Rames squared R. Okay, instantaneous. So this is the equation for the instantaneous power for the pure resistor. Then P equal to half I0 V0 sin 2 omega T. Okay, instantaneous power for the pure capacitor. And also P equal to half I0 V0 sin 2 omega T. Okay, instantaneous power for the pure inductor. Okay, so now look at for the average power. Okay, so a few equation involving average power. So P average equal to half I0 V0 equal to half P0. Okay, the first equation. So you also can use P average equal to I RMS V RMS equal to RMS squared R. Okay, so this is average power for the pure resistor. Okay, so we have 3 to 4 equation here, so you can use. Okay, average power for the pure capacitor equal to 0. So do our average power for the pure inductor. Okay, P average equal to 0. Okay, now look at for the phasor diagram. Okay, actually we draw the phasor diagram from the graph that we sketch. Okay, for the pure resistor, as we said, both current and voltage are in phase because they start from the same point. So both current and voltage are in phase. So when we sketch the phasor diagram, so this is the phasor diagram for the pure resistor. Okay, the current and the voltage are in phase. Okay, alright, then look at for the pure capacitor. Okay, the current lead the voltage by 90 degree or 1/4 cycle. Okay, so this is the graph for the pure capacitor. Okay, current, lead, voltage. Okay, current go first and then followed by the voltage. So current lead voltage by 90 degree. Okay, so when we convert this equation, this graph, okay, into the phasor diagram. So this is the current. Okay, then this is the voltage. Okay, voltage here start from 0. Okay, current here, okay, start from here. Okay, so current lead voltage by 90 degree. Okay, for the pure capacitor, so this is the phasor diagram for the pure capacitor. Current lead voltage by 90 degree. Okay. Okay, next pure inductor. Okay, for the pure inductor, voltage lead current by 90 degree. Okay, voltage lead current by 90 degree or 1/4 cycle. Okay, so this is the value for the voltage and then this is the value for the current. Okay, so the voltage and the current is not in phase because they are not starting from the same point. So since I not start from here, so the graph for the current start from here. Okay. Okay, then voltage are here. So graph phase diagram for the voltage should be here. Okay, right. So as we can see in the diagram, so voltage lead current by 90 degree. Or we also can say that current lag voltage by 90 degree. Okay, ada one ya. Ada voltage lead current or current lag voltage. Okay. Alright, so this is the second part for this topic ya. Okay, pure inductor, pure capacitor and pure resistor. Okay. Okay, now we continue with the combination of circuit. Okay, combination of circuit. Okay, so we continue with the other types of the AC circuit. Okay, so we have the series RC circuit. Okay, we have series RC circuit. Okay, series RL circuit and also series RCL circuit. Okay, now look at the circuit first. Okay, so for the RC circuit, it contain resistor and capacitor only, and both of them are connected in series. Okay, in the circuit. So this is the AC source, yeah. So this is the RMS. Okay, ni VMS R, voltage across the resistor R. Ni VRMS C, voltage across the capacitor C. Okay. Alright, then we have RCL circuit. Okay, series RL circuit. Circuit that contain resistor and inductor only, and both of them also are connected in series. Okay, so this is AC source. This is the RMS. Okay, then we have the series RCL circuit. Okay, series RCL circuit. Okay, we have resistor, capacitor and inductor are connected in series. So all of them will have the same current, IRMS. Okay, so this is the alternating current source, VRMS. Okay, so look at for the phasor diagram. Okay, for the RC circuit, actually we combine phasor diagram for the resistor and also phasor diagram for the capacitor. Okay, for the RC circuit, for phasor diagram for the RC circuit, actually we combine phasor diagram for the resistor and also phasor diagram for the capacitor. Okay, so for example, okay, phasor diagram for the resistor, okay, both current and voltage are in phase. Okay. So phasor diagram for the resistor, so current and voltage are in phase. So this is the current and this is the voltage here, VR. Okay, so this is the phasor diagram for the pure resistor, and then we combine it with the phasor diagram for the pure capacitor. So as we know, for the capacitor, current lead voltage. Okay, so this is the current. Okay, then this is the voltage here, VC. Voltage across the capacitor. Okay, then we combine, we combine both. Okay, we add capacitor, phasor diagram for the pure resistor with the phasor diagram for the pure capacitor. Alright, okay, okay, so kita samakan current dia, kita samakan current dia sebab resistor and this capacitor are connected in series ya, so they will have the same RMS current here. Okay, so kita boleh samakan current dia. So bila kita samakan current dia, so dia akan jadi macam ni. Okay, so this is the diagram. Okay, ni I, okay, ni VR, ini VC. Okay, ni ya, ni samakan, so VR akan di sini, VC akan jadi ke bawah. Okay, ni adalah combination R dengan VR dengan VC. Okay, so tengok dekat RL circuit pula. Okay, RL circuit we combine pure resistor and also pure inductor. Okay, figure for the pure resistor. Okay, so this I and VR. Okay, for the pure capacitor, pure inductor, voltage lead current ya. Okay, voltage lead current. So this is the voltage. Voltage lead current. So current here, so voltage will be outputs lah. So this is the value for the VL. Okay. Okay, nampak? So phasor diagram for the pure for the series RL circuit. Okay, VL, I, VR. So since here we have the VR and also VL, so the resultant must be in the middle here. So this is the V lah, total output voltage. Okay, the resultantnya this one. Okay, and then for the RC circuit. Okay. So okay, for the RC circuit, okay, this is the resistor, pure resistor phasor diagram. Okay, and then this is the for the pure capacitor phasor diagram. Okay, current lead voltage, and then the resultant should be here. So this is the total of voltage lah. Okay, then it's the phase angle. Okay, so here is the phase angle. Okay, so that is how we draw the phasor diagram for the RL circuit. Okay, for the RCL circuit, we combine both phasor diagram. Okay, pure resistor, pure capacitor, and also pure inductor. So we combine all the phasor diagram, and then it become like this. Okay, alright. Okay, for example, okay. So we have the phasor diagram for the pure resistor, I, VR. Okay. Okay, then phasor diagram for the pure capacitor, current lead voltage. Okay, so this is the VC. And then for the pure inductor, voltage lead current. Okay, so this is the VL. Okay, nampak? Okay, so this is the phasor diagram for the pure capacitor. Okay, for the pure inductor ya, RCL circuit. Okay, so this is the phasor diagram. Okay, okay, and then okay, here you look at the value of SC and SL. Okay, if SL is larger than SC, so means that SL minus SC. Okay, if SC is larger than SL, so SC minus SL. Okay, ini we will look at the detail after this ya. Okay, so in this circuit, the value being given is VL is larger than VC because SL is larger than SC. Okay, the resultant is here, the pink one ya. Okay, so because the resultant is here, the pink one, so the total voltage we will get here. Okay, above ya. Okay, above as this. Okay, positive as this. So this is the total voltage ya. Okay, so this is the phase. Okay, or the theta ya. Okay, so this is for the RCL circuit phasor diagram. Okay, once again. Okay, phasor diagram for the RC circuit, combination of phasor diagram resistor, pure resistor, and phasor diagram pure capacitor. Phasor diagram for the series RL circuit, combination of phasor diagram pure resistor and also pure inductor. Okay, phasor diagram for the RCL circuit. Okay, combination of phasor diagram for the resistor, capacitor and also inductor. Okay, now we look at on how to blow up the equation, yeah. Okay, the equation for each circuit. Okay, so now we blow up the equation. Okay, for the total source voltage V. Okay, for the VRMS. Okay, because in this circuit we have pure resistor and pure capacitor. So VRMS equal to square root VRMS squared plus VRMS C squared. Okay, but if you want to write down in the terms of I and R, so VRMS equal to RMS square root R squared plus XC squared. Okay, so this is the question for the total source voltage for the pure for the RC circuit. Okay, for the RL circuit, so we have the VRMS R voltage across the resistor and also VRMS L voltage across the inductor. So VRMS equal to square root VRMS squared plus VRMS L squared. Okay, if you want to write down in terms of impedance, so VRMS equal to IRMS square root R squared plus XL squared. Okay, so that will be equation, yeah, for calculating the total voltage source. Okay, for the RCL circuit, okay. So VRMS equal to VRMS squared plus VRMS L minus VRMS C. Okay. So VRMS L minus VRMS C, yeah. Okay. So this depend. Kalau LC is larger than SL, so VRMS L minus VRMS C. But if VRMS C is larger than VRMS L, so VRMS L minus VRMS C. Okay. Okay, when we write down in terms of the impedance, so VRMS equal to RMS square root R squared plus in bracket XL minus SC squared. Okay, this one for XL is larger than XC. If XL is larger than XC. Okay. Alright, now look at for the impedance Z. Okay, impedance Z for the RC circuit, so Z equal to square root R squared plus XC squared. Okay, for the RL circuit, so Z equal to square root R squared plus SL squared. And for the combination RC and L, so Z equal to square root R squared plus XL minus XC squared. If this SL is larger than XC or otherwise. Okay. Okay, if they ask you to draw a phasor diagram in terms of the impedance, so this will be the phasor diagram. Okay, R at C Z, XL R Z. Okay, Z R at C SL. Okay, SL is larger than SC, so we got this one will be above here. So the total will be above positive axis lah. Okay, Z. So this will be the theta. Okay. Alright, then the angle between the total source V and the current I label as, okay, this one is the phase angle, yeah, the theta or phase angle. So tangent theta or tangent phase angle equal to VRMS C over VRMS X ataupun tangent theta equal to XC divided by R. Okay, ni ya, XC divided by R. Okay. Kalau for RL circuit, okay, tangent theta equal to VRMS L divided by VRMS R. Tangent theta equal to SL divided by R. Okay. Or for the RCL circuit, okay, tangent theta equal to VRMS L minus VRMS C divided by VRMS R. Okay. So, or in terms of the impedance, tangent theta equal to SL minus XC divided by R. Okay. Alright. So, this is for the combination circuit, pure RC circuit, RL circuit and also RCL circuit. Okay. Okay class, so I show you once again on how to draw the phasor diagram for the RC circuit. Okay. So RC circuit is a combination of pure resistor and pure capacitor. So for the pure resistor, this is the phasor diagram. Okay, and then for the pure capacitor, current lead voltage. So this is the current and this is the voltage. Okay, so this is the total voltage and this is the theta. Okay, so this is the phasor diagram for the RC circuit. Okay, for the RL circuit, combination of pure resistor and pure inductor. Okay, so okay, this is the diagram for the pure resistor. Okay, in pure inductor, current lead, voltage lead current. Okay, so voltage will be here, VL. Okay, so the total voltage will be here. So this is the phase angle. Okay, so this is the phasor diagram for the RL circuit. Okay, phasor diagram for the RCL circuit, which is let's say I draw SC is larger than XL. Okay, SC is larger than SL. Okay, so first we draw the phasor diagram for the pure resistor first. Okay, current and voltage are in phase. Okay, then phasor diagram for the pure capacitor. Okay, current lead voltage by 90 degree. And phasor diagram for the pure inductor, voltage lead current by 90 degree also. See? Alright. Okay, and then the resultant in here, SC is larger than SL. So means that VC is larger than VL. So resultant should be here. Okay, so this one is the VC minus VL. Okay, because the resultant is here, so the total voltage is supposed to be below. Okay, so this is the total voltage and this is the theta. Okay, so this is the phasor diagram for the RCL circuit, which is SC is larger than SL. Okay, so when SC is larger than SL, we called it was the RCL circuit with more capacitive. Okay, more capacitive here. If SL is larger than SC, okay, SL is larger than C, we called it was the RCL circuit, which is more inductive. Okay, if SL is larger than SC, more inductive. If SC is larger than SL, more capacitive. Alright? Okay. Okay, next continue with the last part of this topic. Okay, resonance. Okay, this is an extra concept that you must know. Okay. So, resonance in AC circuit is defined as the phenomenon that occurs when the frequency of the applied voltage is equal to the frequency of the RCL series circuit. So, the frequency of AC source is adjusted until it draws the maximum current. So, the frequency of AC source at this instant is the resonant frequency. So, resonant frequency occur when the maximum is current. The current is maximum. Okay, the current is maximum. Okay, now look at here. Okay, the concept. Okay, when maximum current occur. Okay, maximum current occur when XL equal to XC. Okay, XL equal to XC. When XL equal to XC, so XL will minus C or XC will minus XL. So, the only Z that we have is the Z that come from the resistor only. Okay, Z minimum equal to R. Okay, so bila Z minimum, current will be maximum. So, bila current will be maximum, resonant frequency occurred. Okay, resonant frequency occurred. So, when resonant frequency occur, so this is the formula. If they ask you to calculate the resonant frequency. Okay, so FR equal to 1 over 2 pi square root LC. Okay, so this is the equation to find the resonant frequency. Okay, so resonant frequency occur when SL equal to XC. Okay, when SL equal to XC, Z will become minimum. So, Z minimum equal to R. So, current will become maximum. So, when current become maximum, frequency of AC source at the instant is the resonant frequency. Okay? Alright. Okay, now here a few formula involving average, involving power. Okay, so look at for this one. Okay, average power for the RCL circuit. So, P average equal to RMS V RMS R or RMS squared times R, or P average equal to RMS V RMS cos theta. Okay, cos theta is the power factor. Okay, cos theta is the power factor. Okay, or you also can use P average equal to RMS squared Z cos theta equal to PR. Okay, alright. So for the instantaneous power, P equal to IV. For the power, a few formula to calculate the power factor. Okay, first cos V equal to PR over PA, or equal to P average equal to RMS VRMS. So or equal to PR over RMS squared Z, or cos theta power factor equal to R over Z. Okay, so a few equation that you can use in order to calculate the power factor, yeah. Okay, and then for the average real power, PR equal to P average equal to RMS VRMS cos theta. And then for the apparent power, PA equal to RMS squared Z. Okay, so two type of overall RCL circuit impedance. Okay. Okay, this one. Okay, if SL is larger than SC. Okay, for the RCL circuit. Okay, if SL is larger than SC, so here's the phase diagram. Okay, for the phase diagram for the RCL circuit, which is SL is larger than SC, and the circuit is said to be more inductive. Okay, more inductive, yeah, this one. Okay, if for the RCL circuit, okay, which is SC is larger than SL. Okay, SC is larger than SL. Okay, so the resultant will become here. Okay, so Z total above the S axis. Kalau SL is larger than SC, Z total is above ni. This one is above S axis. This one is below S axis. Okay, below S axis, yeah. Okay, this one, if SC is larger than SL, more capacitive. Okay, the circuit is said to be capacitive or more capacitive, yeah. Okay, this one more inductive. This one more capacitive. Okay, so the equation, if SC is larger than SL, so for the V, VC minus VL. Okay, so V equal to square root VR squared plus BC minus VL squared, yeah, in bracket BC minus VL squared. Okay, for the impedance, total impedance Z, okay, square root R squared plus in bracket SC minus SL squared. Okay, for the phase angle, tangent theta equal to SC minus SL over R. Okay, and then VRMS equal to RMS Z. Okay, alright. Okay, now kita tengok a relationship, ya. Okay, this one. Okay, sometimes they ask you to draw a graph to explain the relationship between R at C, SL, Z and with F. Okay, with F, ya, dengan F. Okay, so look at here, a few example here. Okay, the above diagram shows that, okay, the impedance Z of an RCL series circuit depend on the frequency F of the voltage supply, since both inductive and capacitive reactance depend on F. Okay, for the inductive reactance, SL equal to 2 pi FL, so which means that SL is directly proportional to F. So when F increase, SL also increase. So, SL increases with F. Okay, tengok for the SL, this one, ya. Okay, the blue line here. So, SL equal to 2 pi FL. So, from this equation, we can see that SL is directly proportional to F. So, when SL is increased, F also will be increased. So, that's why we got this blue line, ya. Okay, so this blue line represent the relationship between SL and F. Okay, alright, now let's go, okay, look at for the capacitive reactance. Okay, capacitive reactance SC equal to 1 over 2 pi FC, which means that SC is inversely proportional to F. So when F is increasing, SC is decreasing. So SC decreases with frequency. Okay, here, yeah. Okay, from this equation, so as we can see, SC is inversely proportional to F. So when SC is increases, F will be decreases. So this will be the equation of the red one. Okay, the red line represent relationship for the SC with F. Okay, so SC is inversely proportional to F, right? Okay, then look at for the resistor, the green one, the green line here. Okay, the resistance R is assumed to be unaffected with F. Okay, for R, it was unaffected with F because there is no equation of R involving F, yeah? Okay, so R dia unaffected with F. Okay. Okay, kalau for the Z, total impedance here, okay, Z equal to square root R squared plus XL minus XC squared. Okay, so this is the diagram. Okay, something like a quadratic, yeah, the purple one. Okay, so this concept at least you must know and understand, yeah. Sometimes it can come out in the final. Okay. Alright, and then this one, okay, figure 21.9 shows the RMS current I in RCR circuit, varies with frequency. Okay, this one if we want to look the relationship between RMS dan juga frequency, yeah. Okay, so I max FR, F. So at frequency above or below the resonant frequency FR, the RMS current I is less than the RMS maximum current I max, as shown in figure above. Alright, okay. So we have finished discussing topic 6 for alternating current. Okay, so you can proceed with the tutorial and also exercise. Okay, so make sure you do it. Okay, do it for your own good. Okay, so make sure you do it and then turn it in the GC. Okay, alright. Okay, class, so I think that's all for today. Okay, thank you for listening.